Okay, so we will talk about normal subgroup. We will define what do we mean by normal subgroup. So, let G be a group and H, which is a subset of G, non-empty subset of G. H is also a group, I mean induce operated by star. So, H is a subgroup of, suppose H is a subgroup of G. Then H is called a normal subgroup if H is a normal subgroup. This is the definition. Subgroup if H of A is equal to AH for all A belongs to G. This is the definition. If H of A is AH, this is the left coset, this is the right coset. So, in the last class we have seen the number of left coset and the number of right cosets are same. Number of distinct left coset is same as number of distinct right coset. Now, this is telling us the left coset and right coset are same. So, this set is same as this set. So, yeah, that is the definition, and this must be true for all A belongs to G. Then the set, then the group H is called a normal subgroup. Okay. Now, if a group, if G is commutative, then any subgroup is a normal subgroup, because if G is commutative, then abelian, then H of A is equal to H A. This is true for all H and A belongs to. So, all H belongs to G, all H belongs to H, and also A belongs to G. So, if this is the abelian property of a group, if G is a abelian group or the commutative group, then every subgroup is a normal subgroup. But we are talking about in general G is not a, suppose G is not a abelian group, then the definition of normal subgroup is this, if this property satisfy. So, we want this to be left coset is left coset and right coset are same. So, we want this H equal to H A. So, that means these two sets are same. This is not telling us that H must be equal to H of A. No, this is not telling us this. So, this is the group. Okay, if you take a element over here A, then this is a H and this is a same group. If you take same element, this is H A. Now, this is telling us A is equal to H S. That means, if you take a element A H 1 over here, there has to be element over here H 2 A, both are equal. So, A H 2 is same as, so A H 1 is same as H 2 A in that sense. So, this is a subset of this, this is a subset of this. It is not that it will be in the same element, same H will satisfy this, no, it is not that. So, we have to show these two sets are same. So, that means, this is a subset of this, that is a subset of this. So, if a group is a normal subgroup, then we denoted by this as H. This is the symbol of normal subgroup. H is a normal subgroup of G. Okay. Now, we will know a necessary and sufficient condition to a subgroup to be a normal subgroup. That means, the normality test of normality. So, we will have a theorem which is a necessary and sufficient condition for a normality. Test of normality. Okay, so this is a theorem you can say. So let G be a group, non-empty group, and H is a subgroup of G. H is a subgroup of G. Then H will be a normal subgroup. Then H is a normal subgroup if and only if this is the necessary and sufficient condition. What is the condition? Condition is given a G, given a H belongs to H, we take an element from H, then then the X inverse belongs to H for all X belongs to G, and this is true for all H also. So, any H for any H, this must satisfy. So, this is the condition. If X inverse belongs to H, that means X inverse, this is a subset of H. If we can show this, I mean this we have to prove, this is the statement of the theorem, this is necessary and condition, necessary and sufficient, this has two parts, if and only if part. So, if H is a normal subgroup, then this condition must be true, and the sufficient condition, if and all only if part is, if this condition is true for all X and for all such H, then we have to show this is a normal subgroup. Okay, so let us start with the first part of the proof, I mean if part. Suppose H is a normal subgroup, then we have to show this is true, this statement is true. Okay. So, let us try to prove this theorem both the way. Okay, so here is the proof. So, this is the first is if part. So, that means suppose H is a normal subgroup. Suppose H is a, I mean H along with this star is a normal subgroup. Okay. So, then we have to show that statement. So, then how to proceed? Then we take an element X, we take an element G and an element from H, then X H belongs to X H, X capital H, and which is same as this, because this is a normal subgroup. X A is equal to X H is equal to, so left coset and right coset is same with respect to this element. Okay. So, now X H belongs to this. So, this means what? This means X H must be equal to some H 1 into X. Okay. So, we can take this side. So, X H inverse equal to H 1 for some H 1 belongs to H. So, this is H 1 which is belongs to H. So, this implies X inverse belongs to H, and this is true for all X, all H. Now, that is the statement of the theorem. So, that this is the necessary condition. Necessary condition means if H is a normal subgroup, then we have this condition. Now, we have to prove the if and only part, sufficient condition. That means, If this statement is true for all x and h, then you have to show h is a normal subgroup. So, let us try that. Suppose this statement is true for all x and y. So, the conversely suppose the statement is true, that means x inverse is belongs to h, and this is true for all x belongs to G and given h belongs to h. Suppose this is true, then what we have to show? We have to show that it is a normal subgroup. That means, we have to show that left coset equal to right coset. So, this we have to show, and this is true for all x, all such x. So, to show this, first of all we have to show this is a subset of this, x is a subset of this, and then we have to show h x is a subset of this, then we are done. So, let us first try this one. Let us first try to show this is a subset of this. Okay. So, for that let us take an element from this. So, this is basically we can write this as x sum, we have taken h 1. So, h 2 for some h 2 belongs to h. Okay. So, now we can take x inverse both side, x inverse, this will cancel out, and by association rule of the group, these are all star basically, but we are omitting star for simplicity. This is star, x star this, but we are omitting star for the simplicity. This is the operation. Okay. Now, this we know, this is basically from this property, this is belongs to h. So, this will be some h 2 we use, some h 3 x. Okay. So, some h 3 x means this is belongs to h of x, because h 3 is coming from h. So, that means p belongs to x h implies p belongs to h x. So, this implies x h is a subset of h x. So, one part is done. So, x h is a subset of h x. Now, we have to show this is a subset of this. Okay. So, similar way we can proceed. So, we take a q. So, now here we want to show this is a subset of this. So, for that we take a q, we take an element from here. So, now if so, that means q is equal to some h 4 x. Now, similar way we can write that h 4 x. So, x inverse h 4 x. Now, this is basically x inverse, then h 4, then x inverse. So, this is for every x, this must be true. So, this is a member of h. So, x 5, where x 5 is from h. So, this implies q belongs to x. So, if you take a q which is in this set, q is this set. So, this is 2. Now, together with this we can say, and this is true for all, x. So, this implies x is a h is a normal subgroup. This implies normal subgroup. So, this is a necessary and sufficient condition to be a subgroup to be a normal subgroup, this condition. So, So, we will check by this condition whether a group is a subgroup is a normal subgroup or not. Okay. So, now we will prove some result on the normal subgroup. For example, if we have a two subsets H and K subgroup and both are normal, then whether intersection is a normal subgroup or not, that is a theorem. So, suppose we have a group G and we have a two subgroup H and K, this is H, this is K, and both are normal subgroup H this K, both are normal subgroup of G. Now, the question is whether intersection is also a normal subgroup. So, H intersection K, this is also this is a theorem. How to prove this? We can prove using the last result, which is the necessary and sufficient condition to a subgroup to be a normal subgroup. So, this is a subgroup because H is a subgroup of G, K is a subgroup of G, and we know intersection is a subgroup, union is not in general. So, intersection is a subgroup. So, now the question is we have to check whether this is a normal subgroup. So, for that we need to use that result theorem. So, what we need to take? We need to take a H from this set, say this is W set, okay. Say W is equal to H, sorry, capital H. So, we need to show W is a normal subgroup. So, for that we are going to use that necessary and sufficient condition. Okay. So, we take a W from here, and so what we need to show? We need to show X W X inverse belongs to W, and this is true for all X belongs to G, and this is for any W which is a W. So, now the W is nothing. How to prove this? Now, W is nothing but X belongs to W, W is nothing but intersection. So, this implies this belongs to this and small w belongs to K. Now, these both are normal subgroup. So, that means that necessary condition of the previous theorem, this is telling us X W W inverse belongs to this and X W belongs to K. So, this together will imply X W X inverse belongs to their intersection. So, that means by that theorem we can say is a normal subgroup. Normal subgroup. Okay. But union is not a, in general is not a normal, because union itself may not be a subgroup, then the question of normal subgroup will come. Now, we will define what do you mean by factor of a group or quotient group. So, let us define what do you mean by quotient group or factor, okay, or factor group. This is also called factor group. Okay. Now, what is the definition? So, suppose let G be a group, and H is a normal subgroup of G. H is a normal subgroup of G. Then we consider all the cosets. Now, since it is a normal subgroup, then the left coset and right coset are same. That means, H is same as H A. So, in that case we will only talk about the coset, both are, because both the cosets are same. Then we take all the cosets in a set, let S be the set of all distinct coset, with the set of all distinct cosets of H in G. So, that means this set is basically H, which is same as H A. This collection, set of all distinct cosets. Okay. Now, we defined a operation on this coset set. So, we defined a binary operation on this coset set. So, this is basically you want to define S cross S to S. So, how to do that? So, basically we take two coset H. So, we operate with this dot, bigger dot B H, which is nothing but A star B H. Okay. A star B H, and this is we define for all A B belongs to G. Now, this is a binary operator and it is a closure. So, this is a, so write small a, or we can write complete circle. This is a binary operator. Okay. Defined on. So, this is the operator from S cross S to S. So, this we have to show whether this is closure or not. So, now we need to check whether this will form a group or not with the set S. So, just we have to check that. So, the question is S and this, whether this is a group or not. So, for that S is not a non-empty, because H is in X S, because H is a coset, H itself is a coset. So, H is not a empty set. Now, we have to prove the closure property. Now, closure property is okay, because if you take two set, two element from this, if you operate with this, then this will give us A star B H. So, this is also belongs to S. So, closure property. Now, associativity property, if you take H, operate with B H and C H, this must give us what? This is basically equal to H operate with B star C H. Now, this is nothing but again A star B star C H. Now, star itself is associativity property, because G is a group. So, this we can write A H dot B H dot C H, because star itself is associated. So, associativity is there. Now, identity element, H is the identity element of this, because H means E H. So, if you operate E H with anything else, this will give us E star A H. So, this is basically H, and this is true for all A belongs to G. So, this is E H is nothing but H, E is the identity element from that group, E G basically, which is same as E H also. So, E is the identity element of the group. So, this is the H is the identity element of this group. Now, the inverse. So, is the inverse for H. So, inverse for H is H, if we operate with A inverse H, this will give us basically A star A inverse H, this is basically H. So, this is the inverse of this. So, if A is there, A is the element in the group, so A inverse will exist. So, A inverse of H is basically A inverse H. So, this is a group. So, this S along with this is a group, and this group is called factor group or quotient group. So, this is called factor group or quotient group. Quotient group or factor group, and this is denoted by G by H. This is just a notation, this is denoted by G by H. This is called quotient group or factor group. Okay. So, now we will define mapping from one group to another group, and when we call this mapping to be a homomorphism. So, we defined a homomorphic function, homomorphism. Okay, suppose we have two groups G and we have a group G1 G2. We have two groups G1 G2 with two different operators. Okay. Now, we define a function phi from G1 to G2. So, we have two set G set, G1 set, G2 set. In G1 set we have operator star, we have underline operator star, and here we have operator something else dot, or we can say something else. Okay. Now, we say this to be a this function, this mapping is called homomorphism, if and only if this condition satisfy. Phi of, if you take two elements from here and if you operate this, phi of A star B is equal to, so this will go to A will go to phi of A and B will go to phi of B under this mapping. Now, if phi of A star B, so A star B is here somewhere here, if phi of A star B will go to phi of these two. So, phi of A and phi of B, but here operator is different, phi of B, and if this is true for all A B, then this mapping is called homomorphism, homomorphic function or homomorphic mapping. Such a mapping is called homomorphic mapping. Okay. So, this is a mapping from one set to another set, and if this mapping satisfy this condition. So, that means, if we take the phi of A star B, which is same as phi of A, that operator in that group G2 with phi of B, and if this is true for all A B, then it is called a homomorphic function. So, we can have some homomorphic function, like example of some homomorphic function. So, now trivial homomorphic function is everybody is going to E of G2. So, we have a function from G1 to G2. So, everybody is mapping to, this is E of G2, identity element of G2. So, for this we can easily verify this property. We take phi of A star B, which is basically we know E of G2, because A star B is an element. So, this is nothing but E of G2 star E of G2. So, this is phi of A, this is operator on that set phi of B. So, this mapping is a, so what is this mapping is a homomorphic mapping. Okay. Now, another example, this is a trivial example of homomorphic mapping. Another example is, if we take two set Z and G2 is say even integer 2Z. Now, we define G1 to G2 a mapping such that phi of A is equal to 2A. So, this is a mapping from this set to this set. Now, we have to check whether this mapping is a homomorphic mapping or not. So, for that we take 2 elements from here, this is all the plus. So, phi of A plus B, which is same as by definition of this 2 of A plus B, which is basically 2 of A plus 2 of B. So, this is basically phi of A plus phi of B. So, yes, this mapping is a homomorphic mapping. Okay. Now, we can have some other definition like isomorphic. When a mapping is called isomorphic. So, if the mapping is a homomorphic, suppose we have two set G 1 and then we have G 2. Okay. Now, suppose we have a function phi, it is a mapping from set G 1 to G 2. Now, we know when it is called homomorphic, if phi of A star B is equal to phi of A operate with phi of B, then it is called homomorphic mapping. Now, if this mapping is bijective, so this has to be homomorphic and it is bijective. If phi is bijective, that means it is 1 to 1 in on 2, then it is called a isomorphism. Then phi is called isomorphism. Okay. Then if we have two sets, whether there is such mapping exists, then we call two groups are isomorphic with each other. Thank you.